My name is Suil. Oh, sorry. My name is Suil. Today I'm going to talk about an upper bound for the Pascal number and for regular graphs, and about a sufficient condition on the number of vertices in a connected K-regular graph for it to be Hamiltonian or to have a Hamiltonian path. This is a partly joint work with Dan, Rui, and Gashin. In this talk, first some graph-PC conjecture related total domination number and the Pascal number in a certain family of graphs will be given. And then I will show you that the conjecture is true when a graph is for regular by providing an upper bound for the Pascal number in for regular graphs. And then after that, I will talk about when the Pascal number in a connected K-regular graph is equal to 1. And at the end of the talk, some open questions will be given. So before giving the conjecture, let me give you some definitions first. So Pascal in a graph is a set of disjoint paths such that every vertex belongs to exactly one path in the curve. And we are interested in the minimum size of such a curve, which is called the Pascal number. Okay. There are several relationships between the Pascal number and some other graph parameters. So for example, in 1961, already showed that the Pascal number is at most the maximum of 1 and the m minus minimum sum degree of non-adjacent vertices. Another one is if G is out of planar graph, then the nullity of a graph is at most the Pascal number. But today, we're going to see a relationship between the total domination number and the Pascal number. So what is the total dominating set?
By the way, the Orris theorem, is it uses the same as the usual Hamiltonian
right.
test?
Yes. The total dominating set in a graph is a vertex subset such that every vertex has a neighbor in the set. And the minimum size of such a set is called the total domination number. Okay? So for example, the total domination number, well, every total dominating set has at least 2 vertices or nothing. Okay? So the total domination number of a star, so that looks like this. So there are n minus 1 vertices. And so because the total dominating set has at least 2 vertices, so the total domination of star is greater than or equal to 2. And if we choose these 2 vertices, then that is a total dominating set. Okay? So total domination number is at most just 2. So the total domination of a star is equal to just 2. And the Pascal number of a star, but by considering a path cover this path and those m minus 3 singleton paths, then the Pascal number of the star is at most m minus 2. Okay? And in an arbitrary path cover of the star, okay, the path, including this vertex, has at most 3 vertices. Okay? And if there is a path with at least 2 vertices, then the path also has to have this vertex. Okay? So the Pascal number of the star is at most m minus 2. So the Pascal number of the star is equal to just m minus 2. And this is a stupid question, but what is the Pascal number of paths? That's just 1. But what is the total domination number of that one? Total domination number is always greater than or equal to 2, right? But we can actually determine the total dimension number of the path. So for example, when n is a multiple of 4, well, you can partition the vertex set and k disjoint when n is equal to 4k. Okay, so you can partition the vertex set into k disjoint paths with 4 vertices. Okay, and then if you choose 2 middle vertices from each path, then that's total dimension set. So which means that the total dimension number is at most n over 2. Okay, and if there is a total dimension set with size less than n over 2, then some path with 4 vertices, well, the intersections, there is some path with 4 vertices such that the intersection of this path and the total dimension set has just at most 1 vertex, right? So that vertex cannot be the middle vertex by the definition of total dimension set because it has no neighbor. So it must be the end vertex, this or this. But if the vertex is this, then this is not covered. And if the vertex is this, then this is not covered. So there is no total dimension set with size less than n over 2. So the total dimension number of the path when n is a multiple of 4, that's n over 2. Similarly, you can also determine the total dimension number of a path, the other cases. Well, these graphs are easy to compute, the path cover number and the total dimension number. But how about Kinetic graphs? The Kinetic graph is a graph with a vertex set, the all k sets from an n set. And the 2 vertices are adjacent means they are disjoint. So if n is less than or equal to 2k minus 1, then there is no edge. Okay? And n is equal to 2k, then that's just one regular graph. And k is equal to 1, that's just a complete graph. Okay? And when n is equal to 2k plus 1, this is a special case. Well, we call the Kinetic graph the odd graph. Well, when k is equal to 2, so k is 5, 2 is the Peterson graph. So what is the total dimension number of Kinetic graph? Well, if n is large enough compared to k, so for example, n is greater than or equal to k times k plus 1, then what is maybe a good exercise maybe to get the total dimension of that one? You can show that that's total dimension of that one is equal to k plus 1. But if n is near to 2k plus 1, then we don't know. That is still open question. How about the path cover number of Kinetic graph? Well, this is also related to the existence of Hamiltonian cycle in the Kinetic graph. Actually, there is a conjecture that all the Kinetic graphs are Hamiltonian. Quattrell and Avdash show that if the connectivity is greater than or equal to independence number, then it is a Hamiltonian. We know that, right?
By Hamiltonian, you mean there's a Hamiltonian path or?
Hamiltonian cycle, sorry.
Cycle?
Yeah. The graph is Hamiltonian means that there is a Hamiltonian cycle. Hamiltonian cycle means a spanning cycle. Okay, cycle including all the vertices. Well, actually, recently, my friend Hui and my advisor West and I also proved that if the connectivity is less than or equal to independence number, then what happens? Well, see, there was a conjecture, Foucault and Joly conjecture, about if the connectivity is less than an independence number and there is a bound for the graph. And well, actually we settled down. I wanted to give a talk about that, but actually there is nothing else we can do here. So I just changed my mind. There are several open questions in here. So, well, anyway, so the connectivity of a kinetic graph is, kinetic graph are regular graph. That's n minus k choose k. And the connectivity of a kinetic graph is also n minus k choose k. And the independence number of a kinetic graph is n minus 1 choose k minus 1. That is related to Erdős-Colorado theorem. So if you compare n minus k choose k and n minus 1 choose k minus 1, this is greater than equal to this. Well, maybe this is also not that easy to compute, but well, if you compute this, then, well, you may have n is greater than equal to approximately k squared over log of k. So if n is greater than equal to k squared over log of k, then that is a Hamiltonian. Well, but in 2003, her name is Yache Chen. She proved that n is greater than equal to 2.62 kind of k, then the kinetic graph is a Hamiltonian. As far as I know, that's the best part thing so far. So when n is equal to near to 2k plus 1, still we don't know. Okay? And actually, kinetic graphs are vertex transitive. And Labache conjectured that every connected vertex transitive graph has a Hamiltonian path. Okay? And this is a special case, but we still don't know. Okay? So you may also try with that one. Let's come back to the original question. So by checking the path cover number and total dimension number, those two graphs, it seems that there is no relationship between them, because this is greater than this is greater than that. But if we restrict our interest to just regular graphs, some graphic PC conjecture says that there is a relationship. Like a 2i's path cover number is at most a total dimension number. And 5 years ago, De Labina, Leo Pepper, Waller, and my advisor West proved directly that this conjecture is true when a graph is cubic. Cubic means 3 regular. Directly means that the fixed total dimension, they created a path cover satisfying this inequality. Okay? But there is another way to prove this. We just only need to show that the path cover number at most n over 6 if G is a cubic graph with n vertices. Because the total dimension number of a cubic graph is at least n over 3. So if you multiply 2, still that is less than n over 3. Okay. Well, actually in 1996, Bruce Reed showed that if G is a cubic graph with n vertices, then path cover number is at most the ceiling of n over 9. So there is a big gap between them, right? So more generally, for a d irregular graph, total dimension number is greater than or equal to n over d. So if we can show that the path cover number is at most n over 2d, then the conjecture is true for all regular graphs.
Wait, so by the way, in the previous slide, so for cubic graphs, so Reed actually reads the theorem of Bruce Reed will imply?
Yes, because this is n over 9. N over 9 is much smaller than n over 6. There is a big gap between.
Right.
Yes.
What did they do? They had a separate proof? Without
Here?
I mean, the previous.
2007.
This one?
Yeah.
They proved that they did not get an upper bound for the path cover number. They just showed that a fixed total dimension set, and they created the path cover satisfying this inequality. Yeah, so it's different technique.
But it's not really necessary for the conjecture, right?
Well, that's also one way. I mean, that's also good. Actually, that's a better way, and probably. Well, because let me explain why this approach doesn't work. So, well, for the irregular graph, well, we know that total dimension is greater than n over d. So if we show that the Pascal number is less than n over 2d, then the conjecture is true for irregular. However, even for 5 regular graph, yeah, there are infinite many 5 regular graphs with Pascal number is bigger than n over 10. Actually, more generally, there are infinite many irregular graphs. The Pascal number is bigger than n over 2d. So we cannot attack the conjecture with this approach. But however, still working, and d is equal to 4. So we did it. So let me give you a sketch of the proof. Well, actually, just the first part of the proof. Just a couple of years ago, Megan and Martin showed that if G is regular, then there exists a non-trivial optimal path cover. Non-trivial means each path in the cover has at least 2 vertices. And optimal means the size of the cover is equal to the path cover number. So they show that if G is a k-regular graph, the path cover number is at most n over k plus 1. When k is equal to 3, 4, 5. So for regular graph, they got n over 5 as an upper bound for the Pascal number. But this is also best possible. Well, because there is, well, if you have a bunch of copies of a complete graph with 5 vertices, K5 is, we know that that's for regular graph, and so. But if we add the condition connectedness, then we can improve their bound from n over 5 to n over 8. And this conjecture this theorem implies this conjecture. Because if n is less than or equal to 7, I said that it's easy to show that there is a spanning path. Well, I mean, if it is true, then anyway, the Pascal number is 1, so 2 times 1 is 2. So total dimension is always greater than or equal to 2. So this conjecture is true when n is less than 7. And n is greater than or equal to a, so this is less than n over a. So n over a, total dimension number of for regular graph is always greater than or equal to n over 4. So this is true. But is this easy? Well, and so another one is, this is a 7. Can we improve this? Well, this is best possible. Okay. Please keep this question in your mind, okay? I will be back again. I will be back to that question, okay? So please keep this question. So this is easy to show that if, okay.
Yeah, that's just Dirac theorem or something, right? So
right, that is true, right. But can you improve?
Well,
yeah, I mean, anyway, I will be back to the question again. To show that this theorem, so by the lemma of Megan and Martin, there is a non-trivial optimal path cover, okay? And I want to choose such a cover with a minimum number of cyclic paths. Cyclic path means the induced subgraph by the vertex set of paths has a spanning cycle, I mean Hamiltonian cycle. Okay? And if we denote the set of non-cyclic passes and the cyclic passes with the I vertices by capital P sub I and by capital C sub I, and well, the path cover is just the union of non-cyclic passes and the cyclic passes. And the size of the path cover is the number of non-cyclic passes and plus the number of cyclic passes. And the number of vertices and the size of the non-cyclic passes, all passes, and the size of the all cyclic passes.
So when you say the size of cyclic path,
Oh, that's the number of vertices.
number of
Number of vertices, yes. Okay. So if we denote the size of capital C sub I by the small c sub I, well, we need to show this claim. Well, looks like ugly. Well, bunch of numbers here. Well, we may wonder where these coefficients come from. I will explain later. But now let's just multiply 3/4 on both sides, okay? Then that's just P. 3/4, 4 or 3 is just 8. That's 2. Okay, you will have this. Now subtract this part. Then you will have this. And add this. And so there is 2, so we have this 6. This is the same. And then, so can you note that the right side is non-negative?
What is the C5?
So,
Oh, okay.
yeah. So when the size of C is equal to 3, that's minus 3 in here, but here's a 3. This is cancelled. And 2, when the size of C is equal to 4, cancelled. 5, cancelled. And greater or equal to 6 is non-negative. So the right side is non-negative, which means that the left side is non-negative. And now if we separate those two, okay, and this part is just a number of vertices, and now if we take out A, that's the 8 times the size of the curve. And now if we divide by 8, and the size of the curve is at most n over 8. Yeah, so we need to show this. Well, first, let me explain where these numbers come from. We give an orientation on the edges away from the end vertices was a non-cyclic passes, and on the edges away from the vertices cyclic paths. So this is for regular graph. And cyclic paths, we give an orientation like that. But if the edge is inside of cyclic path, then we do not give an orientation. Okay. And now we give a charge 1 to each oriented edge from a path. 1, 1, 1, 1, 1, 1. What is the total charge of that? Oh, sorry. So what is the total charge of this? That's 6. So each non-cyclic path has a 6. Okay. And we give the charge 1504 to the edges instant of 3 cycle, and so that they share evenly. 1504. There is no 1504, but if we add this and this, that's a 1504. Okay. Similarly, 4 cycles 3. So these 2, 3 over 2, 3 over 2, that's 3. And 5 cycles 904. If you add these 2. The 6 per cycle is just 3 over 2. Okay? And we do not give any charge on the other vertices and the other edges. Okay? So the right side is explained. But what about the left side? Well, we give charge on the oriented edges, so we need to distribute the charge to the vertices. Where? Non-cyclic passes. Okay. So we need to have a good distribution of the charges to the vertices of non-cyclic passes, so that every pass has charge, every non-cyclic pass has charge at most 3/4 of the number of vertices of pass. Okay, then this is true. Well, I'm sorry, but the rule that we found is a little bit complicated, and we have a lot of cases to apply the rule. So I'm sorry, but so I just want to skip that part. Sorry.
So how many rules do you have?
There are 5 rules, but each rule has kind of 3 or 4 rules, several rules also. You may find a simpler one. But yeah, well, the rules that we found is kind of complicated. Yeah. Maybe you may find a better rule, maybe to improve the bound n over 8 to maybe n over 9 or something like that. That's also possible, but we couldn't find it. Okay, but instead of that, let's come back to the question that I told you, keep in your mind. Okay, so here lady said that well, n is less than or equal to 7, then well, the connected for regular graph has Hamiltonian path, right? But well, this is better one. Degree 4 plus 4 is 8. So n is less than 8. Then it is a Hamiltonian. So which means that if G is a connected K-regular graph with n most 2k vertices, then it's a Hamiltonian, which means that the path cover number is equal to 1. But the condition to have a Hamiltonian cycle is stronger than to have a Hamiltonian path, right? So, well, here's a better one, slightly better one. The path cover number is at most maximum of 1, and the n minus minimum some degree of this of non-adjacent vertices. So this is, oh, I forgot that one. No, this we can apply this not only to a full regular graph, but also to a general regular graph, right? So we can consider a connected K-regular graph, right? Sorry. So this is 2k, and this is 2k. But this is also possible, 2k plus 1, still 1, right? So we improved it from 2k to 2k plus 1 still. But this is best possible. Still no, there is a better theorem. In 1980, Jackson showed that if G is a 2 connected K-regular graph with at most 3k vertices, then the graph is Hamiltonian. Here is just 3k. But there is a condition to connectedness. Okay? By using this theorem, well, this is just simple exercise by using this one. Every connected K-regular graph with at most 2k plus 2 vertices is a Hamiltonian. How to show this? Well, this is 2 connected, so we only need to care about the case with the cup vertex, right? And you can show that. It's easy. It's easy to show that if a connected K-regular graph has a cup vertex, then it has to have at least 2k plus 3 vertices. At least 2k plus 3 vertices. So this is also best possible. And actually, we characterize the smallest connected K-regular graph without a Hamiltonian cycle. But I told you to have a Hamiltonian cycle is stronger than to have a Hamiltonian path. So what is the maximum number of vertices in a connected K-regular graph or to have a Hamiltonian path? In 1986, Hilbig showed that if G is a two connected K-regular graph with at most 3K plus 3 vertices, so he improved their bound. He improved Jackson's bound from 3K to 3K plus 3. But there are two exceptional graphs. One is the Peterson graph. We know that Peterson graph has no cycle, no Hamiltonian cycle. And the P prime is the graph obtained from the Peterson graph by replacing a vertex in P with just a complete graph. 3 vertices like this.
You mean triangle?
Yes, if we delete this one, then, I'm sorry. So, make it like this. So by using this theorem, we also show that every connected K-regular graph with at most 3K plus 3 vertices has a Hamiltonian path. We know that Peterson graph has a Hamiltonian path, even though it has no Hamiltonian cycle. And by the construction of a P prime, it also has a Hamiltonian path. And if there is a cup vertex V, cup vertex V, such that G minus V has at least 3 components, then you can show that the graph has to have at least 3K plus 4 vertices, okay? So the only remaining case is that the graph has a cup vertex V such that G minus V has exactly 2 components, okay? But we still need to do something more. And actually, to do something more, I use another theorem of Jackson, okay? Then as I bounded, I got the bound to 3K plus 3, but I also want to skip that part. And this is also best possible because we can construct connected K-regular graphs on 3K plus 4 vertices and 3K plus 5 vertices that have no Hamiltonian path. But the interesting is that when K is equal to 3, I mean cubic graph, and when K is equal to 4 regular graph, this is not best possible. Can you guess what the numbers are? Well, when K is equal to 4, if you plug that to 15, right? Then is there a 16 vertex for regular graph, connected for regular graph without a Hamiltonian path? Yeah, I do not believe so. When K is equal to 4, I think that you can improve this found 17. Okay? And when K is equal to 3, you can improve this 14, not just a 12. Okay? Probably it's not that easy, maybe. But anyway, so let me summarize the open questions. So what is the total elimination of a kinetic graph? What is the Pascal number of kinetic graph for or N and K? And I do not believe that the bound that we found is not best. So probably you can improve to maybe n over 9. And there is also a graph satisfying n over 9, but I couldn't find the graph having n over 8, the having the Pascal number equal to n over a. So, and so for more generally, what is the best upper bound for the Pascal number of the irregular graphs when d is greater than or equal to 5? And still, the graphity PC conjecture true when d is greater than or equal to 5. I still don't know. I did not mention about this, but you can also think about this question. So, what is the best upper bound for the total dimension number of the irregular graph? So when d is equal to 3, n over 2 is best possible. And there are infinite many. And d is equal to 4, that's 2n over 5. And 5, I don't know. Thank you.
Okay, thank you very much. Do you have any questions?